Hello and welcome back. For this video we're going to show how to simplify radical expressions. There is a PDF available if you'd like to follow along. First thing I'd like to talk about are the parts of a radical. The index is the number that goes right in here. Now if there's no number that you see there, it's assumed to be a 2, and that's the second root. But we could have numbers like a 3 or a 4 in there and call them cube roots or fourth roots. Since this one has a blank index, it's a square root. And we pronounce this a square root of 4. Now the radical sign is just this part right here, and the number underneath here is called a radicand. A couple of pieces of information you need to keep in mind when you're working with radicals or roots is number one, roots that have an even index cannot have a negative radicand, so you can't have a negative under the radical, and they have two solutions. Roots with an odd index, however, can have negative under the radicand, and they only have one solution. And a third thing is any root can have one or more variables in the radicand. First thing I'm going to talk about is squares versus square roots. So what we have here is a square root of 16, and then we have a set of parentheses, and then on the outside we have a power of 2, or a square. If we do order of operations, we do what's inside the parentheses first. So we're going to undo or do the square root of 16. Now there are two solutions to every square root, positive and negative. However, we're going to take the principal root, which is the positive one for now. So the square root of 16 is 4, and then 4 to the second power will give you 16. So you can see that a square will undo a square root. Now what if we reverse the order there? What if we did 16 to the second power first? So it's inside the radical. Then we'd write that as 16 square root of 16 squared. 16 squared is 256, and then the square root of 256 is 16. So you can see that squares and square roots tend to undo each other. And now the name we call that is they are inverses. Squares and square roots are inverses of each other. Now we are talking about simplifying radicals. So what if we have a non-perfect square or not a square number under the radical? For example, let's say we have the square root of 20, we want to simplify that. Now the square root of 20 can be rewritten as the square root of 4 times 5. And the square root of 4 times 5 can be rewritten again as the square root of 4 times the square root of 5. And the square root of 4 can reduce to 2 square roots of 5. And when we write it like this, 2 square roots of 5, there's really a times in there. Now I want to show you that those two values are equivalent. So the square root of 20 and 2 square roots of 5 are actually equal to each other. So here on the calculator, we're going to show what the square root of 20 looks like. So we'll put 20 in the calculator and press the square root button. You'll see it's not a perfect square. It comes out to an irrational number, approximately 4.47213. So 4.47213. Now let's do the square root of 5 and times it by the square root of 4. So you can see on the screen it's the square root of 5 times the square root of 4, which was 20. And then when we hit equals, you'll see it's 4.47213, just like before. So we know that these two values are equal to each other. So how do we simplify? Well, first we find the largest square factor of the number, in this case 32, and simplify it out of the radicand. So looking at 32, the largest square number that I can think of will be 16. So I'm going to rewrite this as the square root of 16 times the square root of 2. Remember that these two numbers here, when multiplied back together, still have to give you 32, otherwise you've made a mistake. And then proceed to simplify. The square root of 16 is 4, and the square root of 2 is not a perfect square, so we leave it under the radical. So 32, square root of 32, simplifies to 4 times the square root of 2, or sometimes we just say 4 root 2. What if you don't find the largest square factor right away? Well, that's okay. You just keep simplifying. Now here's the square root of 72, and this is a common one that students mess up on. The square root of 72, the first thing they think is, well, a square number would be square root of 9 and times by the square root of 8. And then they'll reduce it, and they'll call it 3 square roots of 8, and they'll leave their answer like that. The problem with that is 8 has another perfect square factor inside. That can be rewritten as the square root of 4 times the square root of 2. And of course the square root of 4 is 2, so we bring the 2 down. And we have a square root of 2 that was not a perfect square staying underneath the radical. And keep in mind, there was already times on the outside, so when we bring the 2 out, we multiply the 2 and the 3 back together, and we get 6 square roots of 2. And this would be our final simplified answer. If you knew your times tables really well, the best way to write this would have been the square root of 36 times the square root of 2, and the square root of 36 would be 6 square roots of 2, and you can see we end up with exactly the same two numbers. So how do we simplify when we have variables under the radical? Well, remember what we said earlier is a square and a square root are inverse of each other. They're inverse operators. They, in effect, undo each other. So the square root of x to the second should equal just x, or x to the first. Now there is a rule that goes along with this, in that we have a even root and we have an even exponent inside, and we end up with an odd exponent outside. For right now, we're just going to ignore that. We'll talk about that in a little more detail during class, and you'll probably see it more often in Algebra 2 or later algebra. So what happens when we have a square root of x to the 6th power? Well, you have to rewrite x to the 6th so that it's in a power of 2, just like this one up here. So if you remember your power rules, x to the 6th can be rewritten as x to the 3rd raised to the 2nd. And 3 times 2 is still 6. So once you do that, then you leave the whole thing under the radical, and you can see that the power of 2 here and the radical on the outside are going to reduce each other or cancel each other out because they're inverses. And this whole thing will end up equaling x to the 3rd on the outside. So short rule here is every even exponent is a perfect square, and you'll notice that the x to the 6th came to the outside half as big because of this rule right here of powers. So what if we don't have an even number exponent? That's quite simple. You just reduce it down to the next lowest even number. So x to the 7th can be written as x to the 6th times the square root of x to the 1st. Now remember what the rule says with these two exponents. When you multiply these base numbers together, the exponents will add. So 6 plus 1 still makes 7. So you still get 7 there. The only difference is now x to the 6th will reduce to x to the 3rd, the same way it did above, and you still have a times radical x to the 1st. Now since this x to the 1st is not a perfect square, it cannot come outside of the radical. It must stay underneath, and this ends up being your simplified answer. Now let's try some where we have both numbers and variables involved in the radical. Now what you should do is treat the numbers and the variables separately. So the first thing you'd want to do is write it as the square root of 12 times the square root of x to the 5th times the square root of y to the 8th. And then you begin simplifying. So x, or the square root of 12, can be rewritten as the square root of 4 times the square root of 3, and 4 is the square number. X to the 5th can be written as the square root of x to the 4th times the square root of x to the 1st. And y to the 8th is already a perfect square, so we're just going to leave it like it is and then reduce it. Okay, so the square root, I'm going to do all the perfect squares first. So perfect square here, and a perfect square there. So the square root of 4 is 2. Now the square root of x to the 4th is x to the 2nd. And the square root of y to the 8th is y to the 4th. And I have some non-perfect squares left over. So I've got a non-perfect square here and a non-perfect square here, which we're just going to multiply back together and leave them under the radical. So I'll have a square root of 3x. So this expression is the reduced form of this expression. So what happens if we have a radical expression that is going to be multiplied with another radical expression? We have a part that's on the outside. This is the rational component, and rational components can be multiplied together. So 2 times 5 will give us 10. And then the irrational components can also be multiplied together. So the square root of 6x to the 3rd can be multiplied by the square root of 2x to the 4th. But we're going to multiply them one at a time, so I'm going to bring my square root symbol over. And 6 times 2 will give us 12. And x to the 3rd times x to the 4th will give us x to the 7th. Complete my radical. And now I start simplifying. Now this 10 is just going to hang out here as a multiplication, so times, 10 times. And then I'm going to rewrite each of these numbers under here as a perfect square component and a non-perfect square component. And 12 can be rewritten as the square root of 4 times the square root of 3. And x to the 7th can be written as the square root of x to the 6th, because I wanted to have even numbers, even exponents, to make perfect squares, and what's left over out of that 7 is x to the 1st. Then I'm going to bring my perfect square components out. So my first perfect square component is the square root of 4, so I'm going to bring my 10 down. Remember, this is all times, so the square root of 4 is 2. And my next perfect square component is the square root of x to the 6th, and the square root of that is x to the 3rd. And then I bring my non-perfect square components back together. So square root of 3 times square root of x is the square root of 3x. And these numbers that are out in front right here just all get multiplied back together. So 10 times 2 is 20 times x to the 3rd is x to the 3rd, and the square root of 3x. And this becomes your final simplified result.